Hey, in this video we're going to derive the mean and the variance of a beta negative binomial distribution. So first I'll develop sort of the intuition behind the beta negative binomial distribution. We'll calculate the probability mass function, and then we'll jump right into the mean and the variance. Here, x is our, x given p, we're going to assume is a negative binomial. Okay, so p is a constant in this case. And as a reminder, r is the number of events or successes, p is the probability of that event, and x is the number of observations past r to achieve r events. Okay. We're going to let beta or p be a beta distribution with alpha and beta, and then the marginal distribution of x is called a beta negative binomial distribution with three parameters, r, alpha, and beta. Now, here's how I derive the probability mass function. So we want to find f of x. Okay? But if we introduce a variable p, but then integrate it out, and p is from 0 to 1, right? Because it stands for probability. So this is the same as f of x, but this joint density or probability mass function can be written conditionally. And then now we know this. This is a beta distribution, and this is a negative binomial distribution. And perhaps I shouldn't have used f and f, or I should have subscript, but hopefully that makes sense. So now let's just fill in what we know. So this is a negative binomial, and this is a beta distribution. So we want to take out everything that is not in terms of p in the p world, which is this and of course the combinations. And then what's left, we combine the p and the r and the 1 minus p, and we get this. Now this sort of looks like another beta distribution if we had the right constant out front. So kind of like this was a beta distribution, we had the right constant. So if we multiply and then divide, or multiply by its reciprocal, then this integrates to 1. And so that's what we do. So I skip that step, and so the constant out front is this. So then the reciprocal of this goes there, and then that's a beta distribution, integrates to 1. So this is it. Oh, this comes down, and then I just rewrite the combinations in terms of gamma and factorials. And this is what's commonly seen in the literature. And I actually think this is what's listed on Wikipedia too. Now the mean of x, we're going to do it in stages. So we're going to use the conditional mean. This is the same as this, but in here, then x given p is a negative binomial, and we know the mean of it's r 1 minus p over p, and then this expectation is in terms of p. So let's rewrite this. Okay, well, since the p is the random variable, then we can use Lotus, and I have a video called Lotus, which is the law of the unconscious statistician, which says that we can take this expectation time in terms of the beta distribution. So here's the beta, and then this is out front. I take the r out front, and of course I take the p up top. That's why I get a negative. Now we combine the p's and the 1 minus p's, and we get this. And I went ahead and multiplied it times 1, right? These all cancel. But I do that because then this is a beta distribution which integrates to 1. And then what's left over is this here. But things start canceling. The gamma here cancels. This right here is alpha minus 1 times gamma of alpha minus 1. So that cancels with this. And we're just left with alpha 1. The r, of course, is here. The beta, same way. This is beta times gamma of beta, so the gamma of beta is canceled, we're left with that. And so this is the mean of a beta negative binomial distribution. Now, to find the variance, I think it's easier to find the second moment first and then use the formula for variance. So here, expected value of x squared is the expected value of this conditional expectation of x squared. And then this in here, expected value of x squared is the variance of x plus the mean squared, right? Because the variance is equal to the expected squared minus the mean squared. So you can do that back solve for just the expected value of x squared. Well, now when we get to here, we know the variance of a negative binomial and we know the expected value of a negative binomial. So we just plug them in. And now this expectation is in terms of the p. And so we're going to get a beta distribution back. So I'm actually going to skip some steps here. So this p comes up to p minus 2, and this is p minus 2. And then we take the expected value, so it's this times the beta density plus this times the beta density, integrated over 0 to 1. And then we get this for this term, and over here we get this term, so the r squared. Now, similar to what we did for the mean, so I skipped a step. Now, to simplify this, things cancel. So here we take 1 away, and then gamma, and then those gammas cancel, and we're left with this gamma of beta plus 1, they cancel, leaving a beta. Here's a gamma of alpha minus 2, so we get this, and the r comes down. Now over here, the gamma of alpha plus beta cancel, the gamma of alpha minus 2, we get this, beta plus times beta plus 1 is from this cancellation. And now we just plug it in. So the variance of x is equal to the expected value of x squared minus the mean squared. And we just calculated this. And so we plug those here. And the mean we calculated on the first page and we square it. Now we start simplifying. I factor out an r, a beta, an alpha of beta minus 1, and this alpha minus 1 squared over alpha minus 2. So this term is left with the alpha minus 1, and then this term, everything, this, since we multiplied it out and it's not here, we have to divide, and then we factored out an r and a beta and these, and we're left with this. And this term, we're left with this. Now, let's simplify. So we have the same denominator. Then we can, when we subtract those, we end up with r times, because an r constant in both terms, factored out. And then this ends up just being 1, alpha plus beta minus 1 over alpha plus beta minus 1. So then we're left with the, 1 times r is r. So this times that, which is what this term is. And so that's the variance of a beta negative binomial distribution. Well, that's all I have for today. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.